perform the three years since 2020 with both of my supervisors, Professor Joachim Penke and Dr. Michael Hölling. And I'm from the University of Oldenburg in Germany. And this work deals with the wake of a floating wind turbine. And it's part, as Sandrine said, of the work package 6, which deals with overall dynamics, mainly actually aerodynamics of a floating wind turbine. So I think there's been already a lot about floating wind, why it's important, why it's a key technology for the future of offshore wind. And actually, when we look at offshore wind turbine, a very important aspect is the wake, the region behind the turbine, which is quite disrupted, have less energy, and we have a lot of interest to understand how it develops in order then to improve layout, to improve design of turbines, and also to test or to have better control strategies in a wind farm. Compared to a conventional wind turbine, a fixed wind turbine, a floating turbine is able to move. It has 6 additional degrees of freedom, free translation and free rotations. And it's kind of a complex system because it's driven by wave, it's driven by wind, and depending on the type of platform, it will move in a different way. Here, I just recall some order of magnitude of the motion of a floating turbine. As I was saying, of course, it's driven by wave, so we'll have frequency of the wave in the spectra of motion. But as a floating turbine can be seen as a spring, when we get it out of its equilibrium position, it will drive back at a natural frequency, which depends on the type of platform. Here, for instance, for a submersible in rotation, you will have frequency of around 0.03 hertz and around 0.01 hertz in translation. And if we express all these numbers in terms of non-dimensional numbers, we can use the Strual number here and also express the amplitudes of this motion based on the diameter of the rotor. And left to give an overall picture, it covers around Strual between 0 to 1.5 overall, and amplitude between 1 to 10% of the rotor diameter. And the big question is, how do this motion impact the wake? Do we have actually an impact of this motion on the wake, whether it's on the recovery, on the transition of the wake, and may also on the wake dynamics? And in order to address this issue, we developed in the University of Oldenburg a setup, an experimental setup, that is based on, or that is composed of a model turbine, the so-called Mowito 0.6. That's a model turbine with a size of 60 centimeters, the diameter. And it's mounted, as you can see here, on a motorized platform, a Stewart platform, that is being used to reproduce motion of a floating wind turbine artificially in the wind tunnel. So without having the need to reproduce waves and kind of like we do in a wave basin. And behind this system, we use anemometers to measure the wind speed of the wake and map the wake. There are different techniques. We mainly used hot wires. As you can see here, this is an array of 19 hot wires aligned horizontally behind the turbine to measure the wind speed, the horizontal wind speed at the hub height. And it's movable, so we could measure the wake at different downstream positions and see how it evolves. So I'll go back on this floating offshore environment. As I was saying at the beginning, it's quite complex. First of all, there is turbulence. The incoming flow that the turbine is seeing is mainly what we call a turbulent boundary layer. So it has a wind speed that evolves with the height, and it features turbulence. The interaction of the wind, the wave currents, and the nonlinear dynamic of the floating platform will raise up to complex 6 degrees of freedom motions. So the turbine is moving quite chaotically, let's say. And if we see real applications, floating wind farm will be installed in wind farms. So there might be some interactions with the first floating wind turbine to one behind. And all this complex problem is kind of hard to investigate in a wind tunnel. So we have to do some assumptions and simplify the problem. And what we did for our test, we mainly consider laminar wind. So we did not account for this complex turbulent boundary layer, which is quite a strong assumptions. But this, we ensure that we only focus on the motion's impact on the wake and did not really investigate that much turbulence. We perform only test using like 1 degree of freedom motions. So testing 1 degree of freedom separately and implementing signal with 1 frequency and 1 amplitude, so harmonic motions. And we investigated the wake of 1 wind turbine. for future application, we could combine all this in order to be closer to reality. And here are a representation of the non-dimensionalized number that is important for this kind of study. So I was mentioning already the Strahl number, the amplitude, and then, as you are also familiar with, the thrust, the tip-speed ratio, and the Reynolds number, which is quite lower in the wind tunnel, but still high enough in order to make sure that the results are close to what we could expect in reality. So I would like to start with some first very simple results. This was measured exactly with the setup that you have on the top. So each point here is a measurement point, and this is the wake flow field, so the mean wind speed in the wake for 3 cases. On the top is our reference, the fixed turbine, and then on the bottom, the turbine being moved in surge, moving in and out in the wind, and on the bottom, the turbine moving from right to left, so swaying, with a given frequency and an amplitude that is very small, around 1% of the rotor diameter. And what we can see here is that in the near wake, we have almost the same field. And then as we move further away, we see that the wake of these two moving cases has the tendency to recover faster. So first, it reaches the region where the wind speed is the smallest, closer to the rotor, here around 4, whereas it's further away, around 6 for the fixed turbine. And also, if you look at in the far field, the wind speed is higher when the turbine is moving, which means that there is more recovery. And the transition also to this far field is reached faster. And another comment, if you look at the size of the wake, you see that it's quite bigger when there is motion, whereas when there is not. So it means that also the motions will engage more amplification of the size of the wake. So this is so I was speaking about this recovery. If we want to quantify it a bit easier, what we can do is we can integrate in the rotor area the amount of wind that is available, and we could see it if you put a turbine here, how much wind is available for this turbine. So if we think of wind farm configuration. This is what has been done here for these 3 cases. So here we will call the recovery, let's say the mean wind speed in the wake, very close to the rotor. You see that for the 3 cases, it's almost the same. And then it goes, and as soon as we go to this transition region, we see that actually the wake of the moving turbine recovers faster, and there is way more wind in the end. Quite big differences, almost 20%. So very in this laminar configuration, great impact of the motions, which when we think about in terms of wind farm application, it's quite beneficial because there is more energy available for a turbine behind. This was tests where we only consider one frequency and one amplitude, but we also played with the frequency, so changing the speed at which we move the turbine. On the left for sway, and on the right for surge, and this is the plot of this recovery, so the amount of wind that is available for a downstream turbine at 10D downstream versus the frequency at which we move the turbine in front. And you see that for sway, it first is very close to 0, so when the turbine is fixed, then it goes up, we have a kind of optimum, and then it goes down again. And here, this is our experimental results, and they are quite similar to some CFD simulation that has been also performed last year and has been published. And this is quite a good way to see that our experimental setup matches with like big, large-scale results. So that is, kind of relevant for large-scale wind turbine. And on the right-hand side, you see the surge case. So similarly, when the frequency is low, we have almost the same trend as the fixed case. And then it slowly goes up, and we have differences up to 20% where the optimum is on a big region, and then it goes down. So actually, when we compare sway and surge degree of freedom, we have some similar differences. But still, in both cases, we have an increase of the recovery for a given frequency. And this is quite surprising, and I think when we think in terms of again, layout optimization, it's kind of beneficial if you have a turbine placed behind it, at least in terms of just energy available. If you look at the loads, maybe it's more problematic. And we spend quite a lot of time with the data that we have in order to understand these results. What is exactly happening? What are the mechanisms at play in order to explain that? The first and also very simple quantity we can have a look at is the field of turbulence intensity. So the same measurements done before. Again, each line is a measurement point, and this is the average turbulence intensity field for these 3 cases. And what we can see for the 3 case, in the very near wake, so close to the turbine, we have 2 strikes of high turbulence intensity. this is quite easy to understand. The wind that is coming here is going very fast. The wind that is coming here is very slow because energy has been extracted by the turbine. So there is shear. And this generates turbulence. And on top of that, we have also the tip vortices that are present. That's why we have these two strikes. And then as soon as the tip vortices start to interact and break down, this region of shear evolves and starts to expand until it reaches the center. And this is what we call the expansion of the shear layer. And what we see is that the point at which it merges is very far away when the turbine is being fixed without motion, whereas it's quite closer to the turbine when we have motion. So we already see that the motion somehow kind of interact with turbulence and generate structures that enable this to happen closer. And also the intensity of turbulence is higher. So this is already kind of a first explanation that all the phenomena are happening closer to the rotor due to the motions. And then we can quantify that or have a better look at what is exactly happening. I will start with the sway cases, so the turbine moving from right to left. And here we look at 3 points in this shear layer that you have here on the top. So on the left, this will be the spectra that we measure at this point for this free downstream position. And you see there is no clear frequency. It's a range of frequency between 0 to 0.6. Here it's non-dimensionalized, where we have quite a lot of energy. And this is characteristic of what we call wake meandering, that the wake starts to somehow move from right to left, and there is a lot of energy contained in this region. If you look at the case where we did not have much impact on the wake, so low frequency, it's very similar. Here I removed all the noise and I put, let's say, the mean. But here I let the noise. So you see that these two are very similar. There is a peak at the frequency at which we excite the wake, but it's quite small. And then if we move further, so we increase the frequency, we see that all this range of frequency merges to one peak, which is exactly the frequency at which we excite the wake. And this is quite, I think, a nice result, which explain that all the non-linearities that is in the wake are concentrated into one coherent structure and also some harmonic. And we can actually visualize them. So here, since we have a lot of points on the line, we can see how the wake moves. On the left, this is the fixed case, measured at 4D, 6D, and 8D versus the time. And on the right is this sway case. The fixed case, you see, the further away we go, the more it starts to develop this kind of meandering. We can see here a zoomed version of this at this position at AD. The wake has this tendency to move from right to left, but it's kind of random. And as we were seeing, it covers large range of frequencies. Whereas when the wake is excited by this sway motion, it will concentrate all this energy into one coherent structure. And the wake oscillates from right to left. And here, I would like to stress that the turbine is being moved with an amplitude of 2% of the rotor diameter, so almost nothing. But in the end, it results into wake motions that are the size of the rotor diameter. So we have a strong amplification of the disturbance that is being imprinted in the rotor area. And we do believe that this has two effects. First, it will enable a higher transport of momentum into the wake. That's why we have more energy available, this recovery parameter. And also, it somehow redistributes the energy more. So you will have like region where the wind speed is high and it goes in. And so it's a double effect, higher transport of momentum and let's say wake distribution. Now, if you do the same analysis for the surge case, it goes even more interesting. It's what is happening for me, it's still something that I don't fully understand, to be honest. So the wake of the fixed case, as before, we have a high region of energy. This is this meandering. Then if we increase the frequency, we'll have, as before, synchronization. All this energy goes into one peak. We can also visualize the structure later on. And then if we increase even further the frequency, so around 0.8, where we actually found our optimum in the recovery, you see that there is a peak at the frequency, but there is also a self-generated mode that appears and some interacting components. And if we look at the complexity of these systems, here we have a lot of modes. Here we have one mode, and here we have a few modes. And this is what we call, in a nonlinear dynamic, quasi-periodic state. And I'm still kind of surprised about that, and because especially we will look at the type of structures that is related to this frequency. So first on the left, so same plot as before with sway. This is looking at the wake at different downstream positions. So again, 4D, 6D, and 8D. Sorry, here I did not put it. When the frequency is around 0.4, when we have synchronization, the wake has this characteristic pulsing structure in the wake. So we move the turbine in front and back, and we see that the wake pulse. This is somehow something that we could expect. But then if we increase the frequency, we see the appearance of this very energetic mode, and actually the surging degree of freedom leads to meandering of the wake. And this is the case for which we have the highest recovery. And there is also a bit of pulsing, but not that much. And again, as for sway, these coherent structures enable the wake to recover faster. So I could also have spoken a bit more about the content of energy that is contained in the structure, but time is missing, so I will go to the conclusion. What we show with this 2.5 years of research is that motions of a floating turbine do impact the wake on the average values, at least when the flow is laminar. Here, I also stress that we did some tests with turbulence, and we noticed, and this is also from a lot of studies, that when there is turbulence in the inflow, the higher the turbulence, the less the impact of the motions. And the question is, what is the region at which we have still a great impact? This is still something that needs to be investigated. We see that through simple motions, coherent structures are being formed in the wake, and they somehow amplificate very small disturbance into big structures. These structures, I was saying, transport momentum, but also even the wake better. That's why we have a higher recovery. And, of course, the impact of turbulence in the inflow is very important to take into account. There are still open questions. For me, this quasi-periodic state, it's still not understood why it's happening. Why does surge generate meandering motion of the wake? We would need to quantify a bit better the amount of transport that is being brought by these motions. With this data, we unfortunately can't, because it's only one-dimensional measurements. And then we have this complex, let's say, state of parameters that we need to investigate further. So the degree of freedom, the excitation, frequency, the amplitudes, the turbulence intensity, the inflow, and potentially the scales of turbulence in the inflow, and try to further investigate all these aspects with respect to these parameters. And finally, try to see how applicable is this study into real floating wind turbine. So I would like to finish with a short video about some tests that we did a few months ago, where we tested, or where we measured the wake of the floating turbine. So here surging, and we measured this with a PIV setup. And by that, thank you for your interest, and I'm open for any questions or discussion. Thank you very much.
Thank you, Thomas, for your presentation. So I see already one question.
Thank you for the presentation. Do you think that in a wind farm controller, this kind of findings on the wake behavior could be translated to engineering models that easily can predict the behavior of the wakes and maybe the loads and performance of wind farms?
It's a good point. I know now they start to work on adapting the engineering model that has actually been developed only for fixed turbine in order to account for motions. But it's quite, we are still in the beginning of that. So this is not a topic I'm working on. I hope that this kind of result can help, at least to validate some models. But if we see that when the turbulence is quite low, we have big impact of motions, for sure we should account for them. And account for, let's say, the impact of these coherent structures on the loads, as you were saying. So how they will do that and how easy it's to do, to be honest, I can't answer, but I strongly believe that we should account for that.
Is your team working on it?
My team is not working on that, no. We are more on, let's say, more ground-based aspect, less engineering applied, but it goes both together. Goes both together.
Thank you. Thanks. Another question, Martin?
Thanks, Thomas. And do you plan to correlate your wake data with the turbine position to explore time lags or hysteresis cycles that you may?
Unfortunately, we can't yet because our measurements are separated. So there is no, let's say, there is no trigger that when we start our measurements, we know exactly what is the position of the turbine with respect to the wake. but we are trying to work on that in order to being able to do that in the future, because for sure it's very interesting to know where is the blade, where is the platform, where is the wake. But this is with this data, unfortunately, we can't.
Thank you.
Thank you.
Hey, Thomas. Question on, you mentioned like the motion of the rotor in respect to the like sway case. You said it's like 1 or 2%. I'm just wondering, is that a design constraint of your experimental setup, or is that representative of platform motions at scale?
Yeah, nice question. It's a bit a mix of both. Let's say first, most of the motions of a turbine are low, let's say small amplitudes. There are also large amplitudes of motions, but then they're happening at lower frequencies, so we focus on a bit higher frequencies. And with this setup, as you could imagine, the fastest we move it, the smallest the amplitude we can reach. So it's kind of a trade-off between the two, and the cases I was showing you are on the boundaries of the setup. But quite surprisingly, it matches also with what we expect in reality. But this study is not, we don't try to take a real floating wind turbine and take exactly the signal of motions and reproduce that. We say we have a spectra of a lot of motions, let's try to break it in easy cases, investigate trends, and then going into more realistic cases, we need, of course, to do some further studies, but at least we try to understand simple cases and their, how do they impact the wake.
That's great, thanks.
Thank you, Thomas, for the presentation. Just a small question. You show a lot of, I think, you correct me if I'm wrong, but all the stuff you showed is experimental.
Yeah.
I think at some point you compare something with CFD results, but did you perform any numerical analysis based on your system or some other system just to compare?
Not, but Mariana is also working on that, so this is an ongoing topic. Mariana was working on free vortex simulations to see how comparable are these results with free vortex codes, at least in the near wake, and see if we can capture some tip vortex dynamics, or also if we can imprint some meandering. But personally, I did not. Okay. But I used the CFD result that have been published in order to compare and see if we have some let's say comparable results.
Okay, just wondering. Nice to see again the wind tunnel of Oldenburg.
Thanks.
Any other questions? So maybe one comment from my side, because we are doing kind of similar experiments, and so far we were using a kind of high turbulent inflow. And we did recent measurements with decreasing the turbulence in the inflow, and we saw exactly the same as you, so the second peak at half of the frequency of the excitation. And so it was also a surprise for us. And so it means that we have similar results, and so we need to discuss on that and try to understand what's going on. Yeah. Okay, so let's thank Thomas again for his presentation.
Thank you.